Welcome to the segment 5 of this week. So in this segment we will talk about the performance. So performance means here we are solely focusing on the training performance, okay, automated mixed precision, and also few compilation practices that we will talk about, which is the minimum requirement for modern day training pipeline, obviously using PyTorch. And these optimizations will lead you to understand how to use or apply the AMP in training, and where to enable torch.compile with single line and understand what it does at conceptual level, and also in the back end what exactly the things to do which will improve the performance from the back end, and also how to measure the combined speed up with AMP as well as other data type. So to identify what exactly is going on here, it's all about the precision, right? So we are talking about mixed precision, and in the previous segments also we have seen that different data types are there for the tensors that we are using in PyTorch. We have AP16, we have AP32, BF16, int4, int8, and so on and so forth. What exactly do they mean, and what are their uses? So you can see that AP32 is single precision and it is 32 bits per number. 32 bits per number we are allocating. So from the name itself we understand that AP16 is half precision and it automatically reduces the size. So that means if my parameters have AP16 instead of AP32, obviously I will reduce the size of the parameter, total parameter, and that will increase the efficiency of storage of my model. But does that always mean that you will get good performance? Not really. Okay. So to discuss this, first try to understand what these data types mean. Okay. So for that we'll go to one interactive page here and we'll understand what exactly they mean. So if float 32 or AP32, so you can see here the bits that are assigned into different segments. So these are 32 bits, and you can see first bit is assigned for your sine bit, next bits 8 bits are for your exponent, okay, and 23 bits are allocated for your mantissa, right? And you can see that how much maximum value that I will be able to gather here, okay. And in A100 NVIDIA GPU will give this much of teraflops at peak performance for this data type, okay. So this is the default PyTorch data type or D type, full precision, and it has the widest dynamic range, and it is used for model weights in mostly in the master copy that you are keeping for, okay. bfloat 16, okay, bfloat 16 has one sine bit, 8 exponent bit, so both 32 and 16 both has same number of exponent bits. However, the mantissa bits are also 7 here, which is highly reduced from the float 32, okay. So total 16 bits, and you can see that 2 bytes per element I can keep. So if I compare the teraflops, peak teraflops performance for your A100 GPU, it is almost double, okay. So this is the brain float 16, and it keeps full 8-bit exponent as the float 32, same dynamic range, it has same dynamic range, but truncates the mantissa, so it will not have the overflow risk because of the exponent retrieval, and it is usually recommended for training D type on mostly the modern NVIDIA GPUs with A100 and H100. Float 16 on the other hand, it is half precision, and you can see that the number of exponents is now 5 bits and 10 bits is your mantissa, and 1 bit sine bit. Sine bit is always 1 bit, and so total 16 bits. So bfloat 16 and float 16, now you know the difference, okay. So you will have less number of exponent bits, which will give you very narrow dynamic range in this case, okay. So values above your 65504 will overflow to infinity, which is basically the overflow data in your Python, and it will require grad scalar to train stably, because if you shoot your gradient values too much, it will actually go to some very narrow data range. Okay, so very high gradient and low gradient will go towards overflow. The TF32 has 1 sign bit, 8 exponent bit, and 10 mantissa, which is used here, you can see. Okay, so 10 plus 8 plus 1, but basically 13 will be dropped in Go. Okay, so TensorFlow 32, it is not a storage D type. You will not get to define your data with TF32 in the PyTorch directly. It's an internal compute format used by CUDA matmul, and basically for devices like Ampere and above, which will take the float 32 or AP32 as input, but multiplication will be done at BF16 precision, which will actually improve the efficiency. So essentially 8 exponent bit will be there, but 13 will be dropped and 10 mantissa will be kept. Okay, and this will be enabled by default in PyTorch if we are using Ampere and above GPU. Float 8 has 1 sign bit, 4 exponent bit, and 3 mantissa bits. Okay, and 8 bits total. So float 8 is kind of used not exactly in the hardware like 8-bit floating point, but it is not used in A100 and other NVIDIA series. It is used only on H100, H200 hardware. It cuts the the VRAM in half by BF16, and it requires very careful scaling because it has very low dynamic range, as you are seeing that 4 exponent bits only possible with float 8. Int 8, 1 sign bit and 7 value, so total of 8. It is not required to have your exponent and mantissa here, so maximum value will be 127, and you will get around 1000 teraflops in your Ampere series of NVIDIA GPUs with int 8. Usually for post training quantization these are used, and at inference time for higher efficiency. So models quantized to int 8 are 4 times smaller than the AP32 with 1% accuracy drop most of the times for image classification and also some NLP tasks. Okay, int 4 is half of int 8. int 4 has 1 sign bit and 3 value, so basically maximum value it can take as 7, and you will have almost similar flops for quantization. So this again it's used for quantization, and usually these modern LLMs enabling with them will be actually reducing the parameter size of huge LLMs like 70 billion parameters or 70 billion model will be able to run in your 48 GB GPU that you have with this quantization. Okay, now float 64 is double precision because you have 1 sign bit and 11 exponent bit, and the rest will be your 52 mantissa bits. You can see the maximum value here, 3.4 into 10 to the power 38, and maximum teraflops is around 19.5. So this is usually default for your NumPy library and really used in deep learning, and mostly for the neural networks it is not used because it uses 8 byte per element, and you can see the teraflops here. Mostly if you can use for the loss accumulation in extreme precision scenarios. If you want to have very high precision maintained in the loss, you can use that, but rather we do not use them. So here you can see the comparison between the different data types, their bits, the bytes they acquire, and also the maximum value they can have, and the teraflops in A100 GPU. And usually which data types are used for training and which data types are used for inference we are seeing here. And if you have older GPUs, we usually use, you can see that float 16 is supported. This is 3F32 is not for your older GPUs, it's Ampere plus. Float 8 is for only Hopper series H100. Int 8 only used for quantization, and extreme quantization you can use for large language models, Int 4, and for scientific computation and for maintaining high precision you can use float 64, right. There are some decision guide that you can follow for your training and inference, because which generation of GPU that you are using, here is a guide. This is just to follow. If you have RTX series, if you have a Hopper series, V100 series, you can use accordingly. Is your model large enough to fit in your VRAM or not? So based on that you can see or choose. Basically the data type that you are choosing and the batch that you are choosing and the Docker memory, that shared memory that you have. So all need to be in sync. So how to do that? We can see one calculation demonstration here. Okay. So you can see that how much VRAM does my model need. If I just want to have a ballpark, let's do the computation here. Let's imagine that I have 7 billion parameters. Obviously I can change here, it's an interactive way of doing things. Just for simplicity, we can see that we have 7 billion parameters for my model. 7 billion parameters, what data type? Float 64, float 32, bfloat 16, float 16, int 8 and int 4. So you can see that the master copy, which has around 60 GB, we can reduce it to 3.5 GB with quantization, and we can use it for the inference with 1% accuracy less. I mean less accuracy in the most of the tasks. Okay. If we talk about inference, that is the case. Now if we go for training, we need 3 times the weights only, because that time we are storing the weights, the gradients and the optimizer values. So basically if I go for training, you can see that 56 GB, which is weight only for inference, increased the size to 168 GB for float 64, and obviously these are not useful for my training pages, but 84 GB is usually required for your 7 billion parameters with float 16, right. Similarly bfloat 16 also will have the same, right. But the difference between these two becomes how you are actually using the gradient, because in the training you have this all the data set, right. So by 3 or into 3, and if you see this overflow demonstration, you will understand what I was talking about by the different data type, right. So if I go for 65,600, you can see that int 8, int 4, float 16 and float 8 has overflowed, but bfloat 16 is still having this dynamic range, or has the capability to resist this dynamic range, and it retains the value. Okay. So overflow is not happening due to the large number of exponent bits that it has. Now you can see that the original value was 65,600. Your very high precision, it's retaining this 65,600. For this 32 is also the same. TF32 is also same, keeping the value same, and bfloat 16 keeping the value same. However, let's say I have 65.857, okay, right. You can see float 64, 32, TF32 is keeping the same value. bfloat 16 is changing this precision, so 0.857 become 0.859, and float 16 has 857. So you can see for low range values, float 16 is good. So if you have very high or fluctuation in gradients, high or low, then bfloat 16 is good, right. So if I have 6 let's say, right, very high value, Obviously B float 16 is still resisting, or it has the same exponent, that's why it's still there alive, right? Obviously int 8 and int 4 will be overflowing till, let's say, very low value, right? So you can just see how this dynamic range actually changes the value, and these changes in fraction will actually get accumulated through each training process or training step, and eventually we will get the error accumulated. So that's why we get that percentage of error difference between by using different data types. Okay, now how much accuracy you want to tolerate, how much accuracy you want to, let's say, negate, or you want to say that this much plus 5% minus 5% accuracy is fine, accuracy loss is fine for me, I'll go with the less accuracy but high performance, that also you can do. I'll go for high accuracy as well as moderate performance, that also you can do. So automated mixed precision, that is exactly what is doing, it's checking or seeing the model, the data that it is using, whether it's image, it's text or whatever, based on that it will actually cast into different data types. So we talked about all these data types. Now to start, by default your torch.compile will be as default the balanced way to do things, but if I want to have faster compilation, and we can change the mode of the model compilation, which can be faster and which can slow also. So if I want to do maxed auto tune, it will have slowest compile but faster runtime, because it will see all the different optimizations data types it want to do in the compilation stage. So it will be slowing down the compilation stage, and it will have the faster runtime, because in the compilation step we have optimized most of the stages and the data. But if you want to have reduced overhead, so it will be faster in compilation, and usually for fixed shapes it is good. Okay, and obviously transformers with many small operations. So which type of models will be benefiting most from this torch.compile? You can see that transformers, because even if with very small operations it can get 30 to 50% speed up, because there are a lot of scope for the optimizations, and also models with many elements wise operations will get fused, and basically their compilation will take some time, right? So we try with torch.compile, and basically if it does not help, we do profiling, and then we launch the complete training stage. Okay, so we talked about mixed precision, why we should not use always FP16, that also we talked about, and the AMP implementation that we can see in the handout also. So in the handout, basically if you see the handout, we will see that in the handout we have the automated mixed precision with B float 16. So you can see that there is one example, worked out example for using different formats, and how much dynamic range they can tolerate, and how much mantissa exponent bits they have. That is exactly what we saw and we discussed, and you can see how much parameter they are going to reduce in terms of size. And then AMP implementation is also there, so you can see that we can set the AMP autocast, which is torch.amp.autocast for your CUDA device, right? And we can enable use GPU. So that way it will automatically do the casting of different data types for your automated mixed precision training. So the performance, you can see that the benchmark is basically done here for AP32, BF16, AMP, FP16, AMP plus scalar, and you can see the different runtimes. Here we are not getting that much of speed up because this is very small model. You can increase the size of the model and you can see the different speed up factor here. Okay, and then you can have this entire torch, the compilation warm up by using torch.compile, right? So how they have increased the performance of the compilation stage, as well as the so you can see that this compilation stage is having how much time, and then in the steady state benchmarking how much time it is taking. You can see the speed up also by using torch.compile. Okay, so the usage is here. So this is the completely compiled version. Okay, in this cell you will be able to see these different modes of torch.compile that we just discussed, and you can see this eager mode, the default mode, and reduced overhead mode, and you can see the speed up also. Based on whatever the model that you can change, the framework will be same, because you will be using this torch.compile to have this entire classifier with the mode that you have set run. Okay, and then the with torch.nograd or whatever the training mode it is there, so it will warm up, and then the compilation will happen. So basically this entire workout example will be applicable for any model that you define. You just change the model and you can reuse that for your particular case. Okay, and then TF32, how it get used if you are using this the torch.cuda as well as cuda.matmul. Okay, as I said, you can use TF32 from this cuda.matmul library, and this TF float will be used, and you can also see how much performance you get. So here our model is very small, and also TF32 is enabled by default on Ampere GPUs or newer GPUs. It is not there in the earlier GPUs. So if you have Ampere GPUs or the latest GPUs, you can work this out and see how much speed up you are getting. So different workout examples are there to explore the different speed up factors, different autocasting factors, as well as precision, mixed precision training, compile to do eager training or the lazy let's say compilation plus setup stage. So different ways to accelerate your PyTorch module as well as training. So these workout examples you should follow along with the slides that we give, and also I'll share the interactive page for your practice. So with this we'll conclude this week and see you in the next week. Thank you.